So in this video, we look at something called the second derivative test. Okay, and we're going to set this problem up with with a problem that we had started in a previous video. If you look at this function, for example, we discovered that there were two critical numbers, or two critical values, x is equal to -2 and x is equal to -1. Okay, and we concluded that there was a quadratic approximation at x is equal to -2, and that quadratic approximation was -3x squared minus 12x minus 20. Okay, and we showed that we can see that there is a graph of that quadratic approximation. Black solid line is the function that we have circled there on the right. That's the black dotted line, and the quadratic approximation is the -3x squared minus 12x minus 20 function. And we can see that at this -2 value, we have a local maximum. So we can see here that at x is equal to -2, our function, f of x, which is the black line, appears to look like this. We can tell at -2 there is a critical point, right? So we know that f prime at -2 is equal to 0. And when you compute the quadratic approximation, we can tell that this is a parabola opening down, because there is a -3, because there's a -3x squared term on the quadratic approximation. We're seeing that here. Right? So what we can say here is that this function has a local maximum, that the function f of x has a local maximum at x is equal to -2. Okay. At -1, the function is doing something slightly different. On the large scale, if you zoom out, the function is doing quite a bit of twisting and turning here. But if you zoom in more and more and more on the value -1, we can see that the function gets closer and closer to looking like this quadratic approximation. And this quadratic approximation at -1, right, the function seems to be opening upward because the quadratic approximation had a positive number in front of the 3x squared, right? And we saw that there was a horizontal tangent line, f prime at -1 is equal to 0. So it's flat, but also the function seems to curve up there. And in this case, we would say that the function has a local minimum at x is equal to -1. Okay, so that's just what is going on with these functions near -2 and near -1. Okay, we can turn this into just these observations about the quadratic approximation. We can turn these into something called the second derivative test. Okay, and so let's try that now. Right, and it involves, of course, the second derivative of the function. So notice that our function was 2x cubed plus 9x squared plus 12x minus 4. And therefore, if you compute the first derivative to be 6x squared plus 18x plus 12, and then compute the second derivative, you will get 12x plus 18. All right. And then if you compute the second derivative at the critical values, which was -2 in this case, you'll get -24 plus 18, which is -6. And we knew that at -2, the quadratic approximation was opening downward, right? That's because the second derivative is coming out to be negative. If the second derivative comes out negative, we say that f of x has a local maximum. Right? And we can see also that the second derivative at -1 comes out to be -12 plus 18, which is a positive 6. Okay? And because it's positive, the quadratic approximation is going to open upward, which means that when the second derivative comes out to be positive at a critical value, that the function has a local minimum at x is equal to -1. So the second derivative test is simply what it says. Take the second derivative, and evaluate it at your critical numbers. And then you care about whether or not that answer comes out to be positive or negative. And sometimes it'll come out to be 0. And then we'll have to figure out what happens in that case. Okay? So this example is illustrating a general result, which is stated here. Okay? That the second derivative test basically says that when the second derivative at your critical point is negative, then your function at that critical point has to have a local maximum. And when the second derivative is positive, the function has to have a local minimum at that critical value. And that's simply saying that so when the second derivative is negative, that your quadratic approximation at that value c, the quadratic approximation is opening downward. It's a quadratic function that is opening down. And so the function, right, even though it's not a perfect approximation, the quadratic approximation is going to be saying that your function is opening downward at that point c, which means that you have to have a local maximum when the second derivative is negative. And when the second derivative goes positive, okay, at c, your second derivative comes out to be positive. That means that your function at that value c is curving upward. There's your quadratic approximation, but you know that the quadratic approximation is not a perfect approximation. Your function may be doing something more shaped like this, but at c, your function is opening upward at that point. So therefore, you have to have a local minimum when the second derivative is positive. All right, so there's the second derivative test. Now it's not always a perfect test, because there is a third case here, that what happens when the second derivative at value c comes out to be equal to 0. And this is kind of a bummer, in the sense that we're going to need to do more work. Okay, and let's look at an example of a place where the second derivative could be 0, but the second derivative test fails. So let's take a look. Let's see, where was that place I wanted to write? Okay, so here we are. I see. Let's add a page below. I'll just start. Okay, so here's an important case. Second derivative test fails. Okay. Let's look at the function f of x is equal to x to the 4th. And the function f of x is equal to x to the 5th. Right, so let's pick the video back up. We're looking at places where the second derivative test can fail. We're looking at two different examples. F of x is x to the 4th, and f of x is x to the 5th. And so notice in this case that the derivative, 4x cubed, in the second case, 5x to the 4th. The second derivative, 12x squared. The second derivative, 20x cubed. Okay, and we can see here that critical numbers of the function f of x, critical numbers are when the first derivative is equal to 0. So that implies that x is equal to 0 is a critical number. And in the case of the other function, critical numbers of f of x, right, f prime of x is equal to 5x to the fourth is equal to 0, also at x equals 0. So we got two critical numbers of these functions. And therefore you can see that the second derivative at 0, 12 times 0 squared comes out to be 0. And in the second case, at 0, 5 times, 20 times 0 cubed, which is also equal to 0. Now this was a case where we're seeing that both cases, the second derivative evaluated at your critical number is 0. Okay, and we said that this was a bummer and that the test is kind of inconclusive because anything can happen here. So notice that the function x to the fourth, right, is a function that looks like this. It's really flat on the bottom. And so if you compute the quadratic approximation, right, at that point, you're probably going to get something that looks like this, quadratic approximation. So this function opens upward, and then you kind of know that there is a local minimum here. But the fact that the derivative came out to be, second derivative was 0, right, it didn't show us that there was a local minimum there, because in the other case, x to the fifth is a function that looks like this, I think. And here we're seeing that if you compute the quadratic approximation, right, at 0, right, oh, I'm sorry, actually this is not what the quadratic approximation looks like. It's just 0. The quadratic approximation will be equal to 0 here, and the quadratic approximation for the other function will also be 0. So you know that there's a local minimum for x to the fourth, but the quadratic approximation is 0 in both of these cases. This one is neither a max or a min, right? So the second derivative equals 0 is not enough to distinguish that there is a maximum or minimum, because in both cases the second derivative is 0, but these functions do very different things. Okay, so here in this case the second derivative is 0, but there actually is a local minimum, but the quadratic approximation is 0. It's flat, really, really flat. The second, the quadratic approximation to the x to the fifth, also 0, so really flat. But this function, since it tails up on one side and down in the other, we don't know that this function is a maximum or minimum, because the function goes up one way and down the other. All right? So this is why we have to be careful with the second derivative test. Right? Sometimes it has a failure case where you can't tell what's actually going on. And that's why we need the second derivative test. The first derivative test when the second derivative test fails. And that will be the subject of the next video.